After watching this video lecture, students will be able to write the correct Lewis dot structures for ions and compounds that contain multiple bonds. So what we're going to do is we're going to look at a more complicated example. We're going to look at the polyatomic ion, CO3, 2-, or carbonate, as you guys may know it. And we're going to just follow our steps. First thing we need to do is find our valence electrons. Okay, so carbon and oxygen are the elements that are part of the molecular structure. Carbon has 4 valence electrons, as we figured out last time, and oxygen, if we count over, has a total of 6 valence electrons. So carbon in this molecule, there's only one of them, so we're going to multiply the electrons, valence electrons, by 1, and oxygen we're going to multiply by 3 because we have a subscript of 3. So we have 4 valence electrons coming from carbon and 18 coming from our oxygen. Now, we don't care about the individual atoms, we care about the total molecule, so we're going to sum the total number of electrons that we have coming from each atom. So 18 plus 4 is going to give us 22 electrons. Now, normally that would be the end of our summation of our valence electrons, but because we have a polyatomic ion, because it's an ion, we have to account for the electrons associated with that kind of structure. So, because we have a polyatomic ion with a negative charge, we're going to add an electron for every charge. So in this case, the molecule is 2-, so that means I need to add 2 electrons. Okay, so that's going to give us a total of 24 electrons for our molecule. So now we can proceed on and start working on the other steps. So just like the last time, step number 2 is going to tell us to put the least electronegative element in the middle, and in this case carbon is the least electronegative element because it's farther to the left than oxygen. Okay, and then oxygen subsequently surround that least electronegative element. We then move on to step number 3 and we bond each of our central elements, our central element to each of the exterior elements. So I've used 3 bonds. Each bond has 2 electrons. That's a total of 2, 4, 6 electrons. Okay, so I've used 6 electrons, so I have 18 electrons left after the bonding has occurred. Now, on step number 4, what we're supposed to do is we are supposed to distribute our electrons to the exterior atoms first. Okay, so oxygen needs 8 electrons to be happy or to have its octet, so we're going to distribute 2, 4, 6 electrons to each one of the exterior atoms. Okay, and the reason why I'm only doing 6 is because each one is bonded to the carbon. So each one of those carbon-oxygen bonds represents 2 electrons. So now I've distributed 6, 12, 18 electrons to the central or to the exterior atoms. Okay, so I now no longer have any electrons to distribute. So now I need to use step number 5 and check if everyone has their octet. Now, if I look around, each of the oxygen atoms has their octet. However, the carbon atom does not have its octet. Carbon only has 3 bonds to it. Each bond only has 2 electrons, so carbon only has 6 electrons. It is unhappy. So how do we do that? Do we have any more electrons to distribute? No, 0 electrons is our sum over here on the right hand side. So what are we going to do? What we're going to do is we're actually going to share electrons. So we're going to borrow 2 electrons. I just took it from this oxygen on the right hand side, and we're actually going to share them and form a double bond between the carbon and oxygen molecule. Okay, carbon now has 2, 4, 6, 8 bonded pairs around it, so it has a total of 8 electrons around it, and the oxygen that I just used to share now still has 2, 4 from the bonding set and 2, 4 from the non-bonding set. So subsequently, all of our atoms now have their octet. Now we can move on to finding our formal charges for each of the atoms and subsequently see if our structure is the best possible. So the way we have to look at our formal charges in this situation is that we have to look at the atoms that are bonded differently as individual groupings. So what I mean by that is the oxygen here and here, notice that they're both singly bonded to the carbon. If you look at the oxygen over here, it is doubly bonded to the carbon. So because the bonding situation is different, you must account for that when you do your calculations for your formal charge. So These two oxygens will share the same type of formal charge calculation, so you only need to do one calculation for those two oxygens. This oxygen over here will have its own separate formal charge calculation, and of course the carbon will have its own unique situation. So, with that being said, we're going to proceed and figure out the formal charge. So, the formal charge for the singly bonded oxygen, so I'm just going to put a little line like that to indicate there's a single bond. We're going to take the same approach we did in other examples. We're going to take the number of valence electrons for oxygen, okay, which we know is 6 electrons. Okay, and then we're going to subtract out the number of unshared valence electrons. So if we look at one of these oxygens over here that are singly bonded, we notice that we have 2, 4, 6 unbonded electrons. Okay, and those unbonded electrons are going to get plugged in right here. Then what we do is we're going to take half of our bonded electrons, and so since there's only a single bond here, we know that there's 2 electrons in that bond, so it's going to be half of 2. Okay, so 6 minus 6 plus half of 2 is going to give us a -1 charge. Okay, so each one of these oxygens here have a -1 formal charge. Now, we can go ahead and look at the other oxygen that's a doubly bonded, so I'm going to designate that with a double bond here. Okay, and once again, we do our calculation. We have 6 electrons minus, in this case, we only have 1, 2, 3, 4 unbonded electrons. So in this case, we're going to put 4 unshared valence electrons, okay, plus half of our bonded electrons, and we know in this case that we have 2 bonds. Each bond has 2 electrons, so that's going to give us a total of 4 electrons there. Okay, so 6 minus 4 plus half of 2, that's going to give us 0. So our formal charge on the oxygen over here is 0. And lastly, we're going to look at our formal charge of carbon. Okay, carbon has 4 valence electrons. All right, it has no unbonded electrons, so we'll put a 0 here, and we're going to take half of our bonded electrons. Remember, there's 1, 2, 3, 4 bonding sets surrounding the carbon. Each one has 2 electrons in it. So the carbon, the number of bonded electrons attached to this carbon is 8. Okay, 4 minus half of 8 is going to give us a formal charge of 0. So, formal charge on this carbon is a 0. Okay, now remember, we're always going to try to have our formal charges be as low as possible. So we need to make sure that we've accounted for all of our appropriate structures. We already did this by looking at if everyone has their octet and if everybody is satisfied. Okay, so now what we need to do is we need to make sure that the overall summation of our formal charges for each individual atom gives us the charge of our overall molecule. So if we look at the original formula we were given, CO3 2- carbonate ion, it is a negatively charged ion. Okay, so 2- is the overall charge. So the formal charges should sum up to -2. So -1 plus -1 plus 0 plus 0, that gives us an overall charge of -2. Now, another thing that we must recognize and notice is that when we are writing Lewis structures for ions, we're always going to put brackets around the final structure and put the charge of that ion on the outside. Some people like to use a smaller individual bracket up in just the upper right hand corner. That's acceptable as well, although usually I'll do the 2 large brackets around it and the charge on the outside.